Okay, so we have audio. This is the start of. So the other thing that bugs me is they changed OneNote. This is a newer version of OneNote than I'm used to. And I can put the quick menu up there for changing pens, but I cannot get rid of the top pieces. I used to be able to get rid of the top pieces, right? The bar across the top and then the menu items. But yeah, if I go into full screen, there's an option to allow full screen. Wherever it got to, no, I don't want to do that. It only shows this. It doesn't show the quick access menu. So
have the quick access menu or the options menu?
I want to keep this list of buttons without.
What if you right there? Maybe a little bit over to the left.
Go to view.
I have tried this, so
Normal view.
sorry.
It's going to be the
That's going to be the normal view. I believe me, I've spent hours trying to figure this out and Googling, and this is the best. I originally couldn't even get the buttons for the pens, but I found out I had to actually make up that menu that made it so that you can put whatever you want there. So that's nice, that's really nice, but it wasn't clear that that's what you had to do. I apologise, I'm talking software, I should be talking circuit analysis, right? So let's start on that, maybe.
So just right click on the free space on the Windows taskbar, click on properties, click on taskbar, then click enable auto hide for taskbar.
Auto, sorry, say that again?
So scroll up a little bit more where the search bar is.
Yeah?
Yeah, and go to the free space, the one and try clicking right there.
I would right click where it says history review help.
Mm-hmm.
Like quick access toolbar, like that. Up.
Right. I don't want to do that. I want to hide everything else other than the quick access tool. So how do I get it back?
You can do try customizing the ribbon.
Believe me, I have tried. So this is figuring out what goes into ribbon
You
and.
have to uncheck the home instead of draw history.
Oh, they're right there.
Oh, so if I so if I uncheck all of those, you reckon it's going to go away? Ooh, that I didn't try that. I suspect then I won't be able to get access to anything. I still got file. It's slightly
There
better.
should be an auto hide too.
You might have to correct it right.
I think it's a click on file. Right click on file.
Oh, right click on file. Okay. And then customize the ribbon again.
So it'll just click on that file.
And click where?
What did you do under customize ribbon? Do a drop down menu? Other side?
Yeah, it just adds other stuff. Okay, I've learned a little bit, but anyway, let's get started on. Thank you for helping that. I appreciate the feedback. It's interesting to hear how engineers and engineering technologists approach problem solving. Right? So what I want to try and show, and I don't know whether everybody felt that. Anybody not pick up a tutorial or two? And I go, Okay, so sorry. It's hard to get through in the middle of and I'll be so I have rejigged the timing of most assignments and labs and stuff just because we missed a week, and that sort of threw all the timing that I'd set up at the beginning out. So I'm hoping that makes life a little bit more bearable. But the things I wanted to get done today are, as it says, mesh analysis continued and nodal analysis will start. I believe we have a break next week, right? Because the Monday and Friday and then the weekend in between is the President's Day holiday. So we're not meeting next week. And the other thing I want to try and get done today is a lab about the voltage divide. The piece of paper you have is a tutorial for both mesh analysis and nodal analysis. And what I thought we'd do is I'm going to do the first mesh analysis problem in excruciating detail, and then I'll get, I think I have 3 rows. I think there's 4 problems. The front row is problem 2. The middle row is problem 3. And the back row should do problem 4. But I'll do, I'll have a go at problem, the problem first, the first problem. So, we've done most of the stuff. The trouble is mesh analysis, nodal analysis, superposition, covenant, a little bit more meatier than everything else we've done. Right? And particularly mesh analysis and nodal analysis is application of a lot of the stuff we've done so far. So the key pieces are passive sign convention. The biggest problem any student, every student has in this class is getting the passive sign convention right. If you get that wrong, everything else falls over. So you have to be very careful that you understand the current for a passive device flows into that positive terminal and flows out of the negative terminal. And that defines the polarity of the current, and it defines the polarity of the voltage drop across the device. Okay, so let's see if we can... Oh, that's the other thing I wanted to talk about. I have released the midterm. And believe it or not, this is the paper you have to pass. You're going to be asked these questions. Now you will notice there aren't any numbers on the paper. There's X, Y, Z, A, B, C, variables, placeholders. So what you're going to have to do, that's interesting use of the, it doesn't show up like that on my screen. And there's 4 topics. There's charge, resistivity, resistance versus temperature, and mesh analysis. And there are multiple questions per topic. Only 2 for mesh analysis. I'm going to ask you when we get on to, I use Discord as my communication mechanism, so you might have to get a Discord account. I'm going to ask you to talk me through how to solve one question per topic. Right? So there's 3 charge questions. I'm going to choose one, and I'm going to ask you to talk me through how to solve them. There's 4 resistivity questions. I'm going to choose one and ask you to tell me how to solve it. There's no numbers, so the oral component is all about process, right? I need to see that you understand what, for example, question 6, what is X doing? What is Y doing? What is Z doing? What is the appropriate equation to use to calculate how long the object is. Right? Once we're done with the oral component, I'll enable for each individual student a webwork version. The webwork version will give you numbers, and you'll need to answer the numerical part in webwork. Okay? Now, you're not quite ready to do these sorts of questions for mesh analysis yet. That's why I'm spending quite a bit of today on mesh analysis. Right. We've gone through mesh analysis, and some of you have actually completed the webwork mesh analysis assignment, but I want to talk through some of the details. So let's do that. I think that's what I want. Right, so let's just, before we do anything else, I want to, so these steps are taken straight out of Professor Broderick's draft textbook, right? And we did this last week. You assign the mesh currents, you identify super meshes, and I'm going to talk about those today. You use Kirchhoff's voltage law on each mesh current. Remember, Kirchhoff's voltage law is the voltage drops around a loop, sum to 0. Then you replace each of the voltages with an expression using Ohm's law, particularly for the resistor voltages. So you get a series of equations, one equation per mesh current, in terms of those mesh currents, not just the voltages. Then you distribute and group by terms, so you end up with a series of equations in terms of I1, I2, and maybe I3, if it's a 3-mesh system. And then you solve the system. Now, another nice thing about Professor Broderick's book is at the end of his mesh analysis chapter, and I believe the book is available. Let me just fire up Blackboard, maybe. Yeah, there it is. Broderick book. Right, so all of this is available. It's a pretty it's a pretty long book, but it covers everything we talk about in this course plus a little bit more. I've forgotten how many pages it is. I think it's a couple of hundred pages. Yeah, 191. Right. So that's available to you in Blackboard. And this is his strategy. And the first, and I'm not going to read through everything, I'm just going to read the bolded pieces and apply that when we go through. So how many meshes are there? That determines the size of the matrices they're going to get. It determines how many unknowns we have. One of the things I haven't talked about is, are there any current supplies? These are, remember, we're applying Kirchhoff's voltage law. Current supplies tell you how much current they deliver. They give you no idea what the voltage drop across them is, 0. So they're a problem. Well, there's two options, right? The first option is, does the current supply touch a single mesh current? Right, so if we've got, let me see if I can, no, I didn't want to do that, let's do it that way. No? Oh, it's all the way over there already. Okay, let's try that. If I've got a current source, right, and that's my IS, and there's my mesh current, and there's no other mesh current flowing through IS. What's the relationship between IS and I1? They're equal. Yeah. So the nice thing about having current sources when you're doing mesh analysis is it gives you one of the answers immediately, provided there is only one mesh current going through it. Right? The problem comes if we've got two meshes right, and now, because, like I said, the current source doesn't tell us what the voltage drop across it is, we have no way of knowing. We can't make a KVL equation for the red mesh or for the blue mesh, because there is a voltage drop across the current source, but we don't know what it is until we've finished the analysis. Right, so that's what the next piece is. So if that's the case, we have to use what's called a super mesh. And a super mesh, in this instance, takes in all parts of each individual mesh, but avoids the current source. Right. The trouble with that is, that's one mesh, one super mesh. So it only gives us one equation. However, when we talk about super meshes, now we also have to, we can also still find another equation. Right? And I think you should be able to see that I've got the red current flowing into the top node that way. I've got the blue current flowing into the top node that way. And I've got the current source flowing into the top node, right? So this is the top node I'm talking about here, right? So I can form a KCL equation from that. I can say red current plus blue current plus current source equals 0. And then I get two equations for the two unknowns, for the red current unknown and the blue current unknown. Now it's important that you look at the directions that I've given. Right? I've drawn the red and the blue. So for the red I1, let's call that I1. Right? That means because that I'm flowing into the bottom of this resistor, that means the bottom is the positive. And because I'm flowing into the bottom of the blue side resistor, that means the bottom is the positive. Now let's look at the green current, right? The green current flows into the positive, right? So I'm going to add that one in the equation. So if that resistor is R1 and that resistor is R2, then the equation for the green current is going to be VR1. Right? I'm flowing in. Then I need to go round, and now the green super mesh is flowing in to the minus side of R2. So I need to subtract R2. So that's what gets us our KVL equation, and then the KCL equation is the other one that I said. So I1 plus I2 plus IS equals 0. And obviously we'll have to apply Ohm's law to turn VR1 and VR2 into something in terms of I1 and I2. Okay? So the reason, or the issue is, as soon as you see a current source in the circuit, one of these two things is going to apply. Either it's a freebie and you get an answer immediately, or it means you have to make a super mesh and use an extra equation, which is going to be a KCL equation. Right? This equation down here, this equation here is KCL. We've got to figure out the right way to use the laptop. It's a bit hard writing up like this. And I could flip it back, but then I'd probably need the keyboard. Anyway, we get that. Okay, so let's just continue on through the detail. So the next thing that we haven't looked at much so far is, are there any dependent supplies? Right? Remember the independent supplies, are usually like that if it's a voltage source, or like that if it's a current source. Sometimes you get a battery as an example for a voltage source. But they're independent. They have a value regardless of anything else. The dependent supplies are diamonds, right? And you can get dependent current sources and you can get dependent voltage sources. So make sure you look for them. Dependent sources have a control variable. The biggest mistake I see people make is oftentimes I write the control variable as either Vx or Ix. It's not so much of a problem with Ix, but oftentimes the control variable will say something like, for example, 3Vx, and it'll be beside a dependent current source. People look at 3Vx and don't see the x. So they read it as 3 volts. And then the equation for using the dependent current source makes it look like a voltage source. Right? They just use it as a 3 volt voltage source. So be careful. Make sure if there is an X there that you see it. And then as the point 3 says, figure out where that control variable is measured from. It'll be identified somewhere in the circuit, but make sure you identify it. Then write the equations and then solve the system. Okay? So let's try and apply that to this. The other thing I would say is this first one is easy because I just want to do it as a demonstration. When you finish doing the analysis, reread the question. Right? Sometimes the question is asking for something other than the mesh currents. You probably need the mesh currents to get the answer, but you need to maybe do one extra step. Usually you've got to use one of the mesh currents to find a voltage drop across one of the resistors. Right? That's usually what the question is going to ask. I don't do that to trick you, but it seems to trick students without me trying. So I try and make it obvious that I'm not, that to make sure you read the question. Okay, so step 1. Let's go back to our step 1. Assign mesh currents. Right, so we've got a... Oh, sorry, didn't I get you on? And I'm going to go around this way. Right, so there's I1. And then I am deciding which direction these things go. You can decide whichever direction you like. It doesn't matter. Provided you're consistent, you can choose going one way or the other. The only time it matters is if the circuit already has a polarity defined. Like I said, oftentimes I'm going to ask you for the voltage drop across one of the resistors at the end. If that voltage already has a positive and a negative defined, you're best off making sure that the mesh current that flows through that device goes into the positive side of that device, so that it matches the passive sign convention. And I'll check the 3 questions. We'll have a look at that to make sure. So I'm just going to go clockwise for all 3 of these, right? Like I said, I could go counterclockwise, I could alternate. It really doesn't matter. Right, so there's I1, I2 and I3, and the next item on the agenda, should probably try and keep that, but let's see. So use KVL on each mesh current. So KVL. I'm just going to, I should have probably identified them, right? Let's just call this VS. Let's call this R1. This is R2, this is R3, this this is R4, and this is R5. And the other thing I forgot to do is to make sure I identify the polarity in terms of the passive sign convention. Notice R2 has opposites because of the direction. That is okay. And R4 is going to have, I wish I could write, but it'd be wonderful. R4 also has alternate or different sign conventions for VR4. Right, so now my I1 KVL is going to be plus VS plus VR1 plus VR2 equals 0. Okay, and then let me just see if this works. Maybe. There we go. And then I2 KVL is going to be VR2, and now I'm using VR2 in terms as if I am looking from I2. So I'm going into the positive again, and plus VR3 plus VR4 is 0. And then my I3 KVL is, this time it's just VR4 plus VR5 equals 0. So now I just need to apply Ohm's law and get those equations in terms of the unknowns, the mesh currents. Right, so this one, and I'm going to change VS to 10 volts. So it's 10 plus 5 times I1 plus 6 times. Now I1 and I2 are going in the opposite directions. Right, so it's I1 minus I2. And that equals 0. And then VR2 is going to be again 6, but this time it's I2 minus I1. So you'll notice that the blue VR2 and the red VR2 do have opposite signs, right? Because one of them has the positive at the plus and the negative at the bottom. The other one has the positive at the bottom and the negative at the top. Right, so, and then VR3. Right, so then it's plus 2 I2. And then VR4 is plus 4 I2 minus I3 equals 0. Oops, 0. And then the last one, VR4 is 4 times I3 minus I2 plus 4 times I3 equals 0. Okay, I think I've found a flaw in my cunning plan of folding the keyboard back, but we'll unfold it and get it later. Right, so now I just need to distribute in group-like terms, right? So here I've got, I'm going to do the red one down here, so just so I've got some space. So it looks like it's going to be 11 I1 minus 6 I2 equals minus 10. It's best to get the constants on the right hand side of the equation, and then it's minus 6 I1. Then how many I2s? We've got 12 plus 12 I2, and it's minus 4 I3, and there are no constants, so 0 over there. And then it's minus 4 I2 plus 8 I3 equals 0. Right, now I can put that into a matrix equation, maybe. So in the constants I've got minus 10, 0 and 0. In the unknowns I have I1, I2 and I3. Oops. And I have, the tricky part now is some of these equations don't have one of the variables. So make sure you get the coefficient in the right column. Right, so 11 minus 6, 0 for the first one. Minus 6, 12, minus 4. Now, I was about to write minus 4 here, right, but that's the coefficient for I1, and there is no I1, so there should be a 0 there. So then minus 4 and 8. When there are no dependent supplies, a nice check of your matrix is it should be symmetric. Right? If there are no dependent supplies. Dependent supplies throw that symmetry off, and this is a simple one, so there's no dependent supplies. Okay, let's see if I can do that. And go there, maybe. There we go. I'm going to fire up MATLAB, maybe. There we go. So if you have the disk space, I recommend you install, you all have access to MATLAB for your home computers. So I recommend you get it if you like using it. You can use the Citrix server as well if you don't have access. You can use the machines in here. Right, so I'm going to do a new script, and it's probably big enough to see, isn't it? I'll just make this full screen. Right, I'm now going to make an A matrix, and I'm going to put a semicolon at the end. MATLAB will complain. You can see that the equal sign is highlighted. It will complain if you don't terminate the line with a semicolon. In MATLAB, if you don't put a semicolon at the end of the line, it'll print that out, the result of that expression. Which sometimes you want, sometimes you don't want. Okay, so let's go back here. So we want 11 minus 6, 0. Right, so 11 minus 6, 0. Minus 6, 12, minus 4. Minus 6, 12, minus 4. And then it's 0, minus 4, 8. Oops, wrong one. 0, minus 4, 8. Right, so there's our A matrix. Our B vector is minus 10, 0, 0. Oops. I didn't want to do that. Let's try that. And save as. Yeah, so let's save this as, what do we want to do? Call it CET236. And then our answer is going to be a B or int A times B or int A times B or now I can do RF AB. Right, and let's just run those and see what happens. Right, and they all, thankfully, get the same value. I1 is minus 1.3514 amps. I2 is 0.8108. I3 is minus 0.8108. I3 is minus 0.4054. And remember, RF returns the full matrix, so we're really only interested in the right-hand column. The reason I'm doing RF is I find doing these solutions on a calculator easier to use the RF function on the calculator than doing an A matrix, a B matrix, and then doing the multiplication. That might just be me. Any questions about any of that? Okay, so let me just have a quick look at the other questions here. Right, so here's one. This one is asking for IX. And you'll notice that IX is not going to be a single one of your mesh currents. Because IX is in a branch that probably touches two meshes, IX is going to be either the sum or the difference or some combination of that between the two mesh currents involved. You will notice there is an independent current source. So what does that mean? Let me see if I can pick on someone. Am I? Are you here? Yeah? No? No, am I? Okay, we'll try Daniel. Where's Daniel? He was there. He's left the room. And I don't have a picture of Jason. Hey Jason, do you know what the...
We already know one of them, right?
Yeah, exactly. Right? We already know one of the next ones. Because that's an independent current source, and we're going to draw a mesh current either going clockwise or counterclockwise, I'd suggest going clockwise, just so it's going in the same direction. That'll get you a freebie. Alright. Let's have a look at the next one. Okay, so this one's a little trickier. This one has a dependent source, right? And you'll notice what I said, 8Vx. It is a voltage source, but the mistake people make is thinking that that's 8 volts. It's not 8 volts. Vx is up here. Yeah? It's 8 times the value of Vx. So when you're doing the equation, right, you would just write 8Vx for the kVA, but when you come to convert it to using Ohm's law, you then have to say, well, what's Vx in terms of Ohm's law? And Vx is going to be nothing but I1 R2, right? So Vs2 will end up being 8 times 4 ohms times I1, okay? And then let's have a look at the third one. And again, the third one just has a swap, and you've got Vx there, and there's the definition of Vx. Notice, the other thing to notice, actually there's two of them on this one, maybe on question 3 as well. You've already got some polarities defined. So if you have some polarities defined, voltages across passive devices, make sure those you try and make the passive sign convention apply when you define your mesh current direction. Right? You can do it counter to those, but it gets confusing because there's a minus sign that always gets in the way. The biggest mistake students make is often to do with the minus sign. And the reason is because of the passive sign convention. Okay? So if I can get the front row to do question 2, the middle row to do question 3, and the back row to do question 4. Have a break if you want to, and we'll come back in about maybe 15 minutes to see how you go. You got a question? The first one. This one? Want me to leave that up there? Yeah. Okay, I can do that. Everybody happy with that? Yeah? Okay. I'm going to take a quick slug of coffee. I will be outside.
how it should be, so it wasn't.
Yeah. Right, so you define your ongoing same. No, no. Well, you've got out there already. So that tells you 3x is just 4x. So 3x is 60 centimeters of the inch. Okay? Does that make sense? Well, I always make sure that if you
Well, no, it's just, full-time right now, so,
It still does kind of like break it down. Almost the bus stop, and it's like really fun.
Okay, so I'm going to ask the front row to talk us through how we do question 2. And the first thing I will point out is we're solving for IX. Right? So we start with Maxwell? Yeah? You want to start us off? How do we start? Right, so we define the mesh currents. Right? And I'm going to do it this way. Again, it doesn't matter which direction. The only reason it might matter, particularly for this one, is because IS is going in that direction, and I want my I1 to match up. Okay, and I'm going to go, I also like making sure I know the polarity of all the devices with respect to each of the currents. Now, with passive devices, you get to choose the direction of the current flow, and that chooses the polarity because of the passive sign convention. You don't get to choose the polarity with active devices, right? So this one here is an active device, and so you have to have the same polarity for both I2 and I3. And then I3 has a plus and a minus. Okay. So sorry, I don't know your name.
My name is Marcus.
Marcus, could you take us to the next step? Can you tell us what KVL? Right. So,
I1 will just
that's microamps, yes.
So obviously we could perform the microamps since there's
Exactly. So that's our freebie. Right?
and then for current I2, it would be DLC plus
Okay.
And then for current I3, it would be minus the voltage, minus VS plus VR.
Equals 0. Very good. Okay. Sorry, Jack. So you're next. What do we do next? Okay. Yep. Okay, so 4700. I2 minus I1. Okay, and the next one? Right. And I think that's the next person's name, but I'll get them. Yeah. Right. What do we need? Yeah. Okay. So yeah, we've got the equations now, so what do we do now? Okay. Right, so the nice thing we have here, right, is we already know I1. And the nice thing then is both of these equations are just in terms of one variable. Okay? So yeah, we can write out the blue equation as I2 minus 400 by 10 to the minus 6, right? That's a microamp because it's a mu, and plus 3900 I2 plus 12 equals 0. And I'm just going to continue doing the algebra, so correct me if I'm wrong. I think that's 8600 I2 on that side, and that equals minus 12 plus 4700 times 400 by 10 to the minus 6. So I2 is minus 12 plus 4700 times 400 by 10 to the minus 6 on 8600. So minus 12 plus 4700 by 10 to the minus 6. So minus 12 plus 4700 by 10 to the minus 6 and that's on 8600. And I just want to see a few more decimal places. Right, so it's minus 1.395. I forgot a 400. I did. You're right, I should have had a 400 in there, shouldn't I? Thank you. So there we go. 1.177 to four significant figures. Milliamps. Minus 1.1. I'm just going to right, so our I2 let's just see if we can grab that. Right. No, it's nothing like that. I thought I could put it so it's minus 1.177 milliamps. So I could have done that instead of converting the kilo ohms to ohms. I could have kept it in just kilo ohms, and then the only difference in the answer would then be that the currents I get will be in milliamps rather than in amps, right? So they're out by a factor of 1,000. Some people prefer using all the zeros, some people prefer keeping everything in kilo ohms. The only trouble is and it didn't impact this question. The only trouble is when you get resistance values smaller than a kilo ohm. You have to make sure that you then write 0.22. But it didn't impact this answer. And then the I3 equation, right? We should just be able to write that as I3 equals 12 on 4700. So that's 2.553. Oops. Looks okay. Any questions about question 2? Okay, let's go with the middle row. Now, the next two are trickier. They're trickier for... Oh, sorry, you're right. Very good. What was the question? Solve for IX. Thank you. So, IX. Let's, I think I've used all the colours. Oh well. So the question is, let's go with, what is IX? Right. So let's figure out what IX is. IX is equal to, now I3 is going in the same direction, so it's I3 minus I2. Right, I2 is going in the opposite direction. So that's going to be 2.553 minus negative 1.177. Because I'm looking at the I'm looking at the direction of I1 is going in that direction. Right? Well, it's I3 is going in the same direction. Right? Because it's going in the same direction, it's going to be the positive one. And because I2 is going in the negative direction, in the opposite direction, it's going to be subtracted. What was it? 1.177? Is that what I had? Oops, I keep hitting that button. I should stop hitting that button. Sorry? Okay. Sorry, what was the question?
Not for the IX, I mean for the 4,700.
Yes, that's right. So because I have to flow into the negative, also is the back foot. So then that's, was it 1.177? And that equals, let's just go with, so it's going to be and minus that number there, 3.948. And make sure you get the right units. Okay? So like I said, I do it, students do it, answer the question. So the next two are a bit more complicated. And as I was going to say, they're a bit more complicated for a couple of reasons. Well, this one is only complicated for one reason, and that's because of the dependent source. Right? The question 4 is complicated for another reason, in that it has kilo ohms instead of just ohms. Okay, so can I get the Jason, do you want to start with defining the mesh currents? Clockwise for both of them? Okay. So there's I1 and there's I2. Now I think that's correct, because you've already got some polarities defined, and you want the current to flow into those positive items. Okay. So next, can we do the next step? Well, actually, let me go. I should have done that when I drew them, right? So that's positive. That's positive. That's negative. That's positive. That's negative. That's positive. That's negative. That one's already defined. Okay. So now let's apply KVL. Oh, there's something's I1 equals yep. Right, so yeah, both of those are going into the negative. I don't know why it's decided to slow down a bit, but anyway. Okay, so next up, can you, now we've got to apply Ohm's law. Okay, so we'll start with the red equation. Sorry, 5I1, yeah, plus 4I1, all times I1 minus I2, good, plus 12 equals 0, good, and the blue equation, 4 times I2 minus I1, plus 2I2 plus 8I2 minus 32I1. Let's just go into that. So it's 8Vx, and Vx is 4 times I1. So 8 times 4 times I1 is 32I1. Yep. Minus 12, and that equals 0. Very good. So next along, can we do the distributing group-like terms? Mm-hmm.
equals negative 12.
Equals negative 12. That's good.
For the second one, negative 36 I1.
Negative 36 I1. Okay, that's right. 14 I2, yeah. Right, so I think it's got to be plus 12. Yeah, I think that's right. Okay, so now we can do a matrix equation. The next person along, can you tell us what the matrix equation is? Uh-huh. Okay. So let's see if we can put that into something up here. So this is, I'll make a new one here and we'll call this sheet 2Q3. And our A matrix is 13 minus 4 minus 36, 14. So 13 minus 4 minus 36, 14. 14. And our B vector is minus 12, 12. And then our RF is a RFRB, and we should be able to run that. And we've got minus 3.158 and minus 7.263. Minus 3.158. Can't quite read it there. And minus 7.263. And both of those are in amps. Okay, make sure you get the right units. And let's go back and read our question. So the question is, find V out using mesh analysis. So I follow one of the pages I follow on Facebook is called Engineering Memes. And there was one recently that one of my former students posted or reposted, which is the statement is, you got the right answer, but you didn't use my method. Half marks, right? And I actually responded to my former student, right? If the question asks you to use mesh analysis, I don't care what the answer is. What I care about is whether you know mesh analysis, right? You could solve it any other way. And if you're into it, I recommend you solve it another way and check your answer, right? But the thing I'm interested in is whether you understand mesh analysis, not really what the output voltage is. Yeah. So the output voltage here is I2 R5. And I'm just going to kill that for a second. See if that helps. Because I'm getting a lot of lag for some reason. Okay, and so our I2 was minus 7.263. And our, so what's that? That's about 57 and something. So let's get our answer. And then the answer is going to be Q3. Now it's 2, 3, so it's the bottom entry. We want I2 times 8. So it's minus 58.111. Yeah?
I just have a question about earlier as well. How do you get 32 to
Okay, so the second voltage source is, that's VS2. Right? VS2 equals 8 times Vx. Ooh, sorry, I keep hitting, I have to disable that top button, that's what the problem is. I'll do that when we have another break. And the Vx is up here, right? So that's going to be 4 times I1, right? So it's going to be 8 times 4 times I1. And that's where we get our 32I1 from. You should notice that our matrix is no longer symmetric, and it's because of that extra 32. Right? You can see if that extra 32 weren't there, what you would have is you'd have a different voltage on this side. It would just be if it were an independent supply, that 32 would be with this number here would go, and you get minus 4 and minus 4. But because that dependent supply is there, it alters the symmetry. Does that answer the question? Yeah? Okay, so let's go to the back row. And again, we're interested in finding V out. So don't let me get away without finding V out. And let's start here, and you can tell us how to find the mesh currents. Yep, I think that's a good thing. I should have redrawn these so that V out was upside down just to confuse everybody, but so then we've got, that's the polarity with respect to I1, and they're the polarities with respect to I2. I didn't need to draw the ones for R5. Okay, that looks good. So let's so next question, can you tell us to apply KV, show us how to apply KVL for the I1 mesh.
I1 10Vx plus VR1 plus dx
Okay.
of VR2.
And that's correct, right? I could have written VR2, but because we've already got Vx defined, we might as well not throw another variable in there, so just use Vx as it is. That's good. Okay, next one. And the, you can, sorry? You're correct. Right, because that is flowing into the negative side, that should be a minus 10 dx. Okay, thank you. And then KVL, I2, keep going.
Flow plus 10 dx plus VR3 plus VR4 plus dx.
Yep, that's good. Okay. So, next person, can you now apply Ohm's law and get us to the next step? Sorry, say that again. So 10 times. Sorry, I can't hear. Plus I? Well, it's going to be Vx, right? So Vx is going to be 2000 or 2 times I1, I think. Right, so because Vx is equal to either 2000, actually it is, it's got to be 2000 times I1. Oh, sorry. I'm being stupid. You're right. Let's start again. I thought you were talking about Vx. Sorry. So, start again. Try again. Negative. Right. Well, okay. So, we've got to figure out what Vx is in terms of the current, right? So that means we need to know what Vx is, and this is what Vx is. So when I move from here down, actually down to here, I need to put in Vx in terms of what the current is. So it's going to be 2000 I1. Okay? And now we've done the first term, so let's go on to VR1. Right, that's... So, I'm gonna use all the thousands. I could have written this as minus 10 times 2 times I1, if my, but it's not going to, I think it makes more sense to use the full ohms, right? So I'm going to write VR1 as 1000 I1 rather than just 1 I1. Okay, just to get the scale right. Okay, next one. Right, plus 2000 I1. Right, and then it's I1 minus I2. Yeah? That's for this one here. And I think, and we've already done the 10 dx at the front, so I think then that just equals 0. Let me just get rid of that. Okay, next, so the KVL for I2. Yep. And then that's actually a Vx. I didn't draw it properly. So that should be a Vx. So that's going to be the same as before, but positive, right? 2000 I1. Plus 3000. Now it's the other way round. Yeah, I think it's I2 minus I1, because we're looking at it from the I2 direction. Plus 4000 I2. Plus 5000 I2. And I think we've done. So that equals 0. Okay. Michael, do you want to do the next step? So we want to distribute in group-like terms. Sorry? Right, so this one's going to be minus 20,000. And we're looking for I1 coefficients. So there's 1,000, 2,000 and a 3,000. So what's that going to be? That's 26,000? Sorry. No, because that's a negative. That's my fault. Sorry. Right, so it's going to be minus 20,000 plus 1,000 plus 2,000 plus 3,000. So that's minus 11,000, is that right? 14,000. It's 6, you're right. Minus 14,000. I'm making so many mistakes today. Sorry, Michael. Okay. So what's next? You've got to get I2, I think. Well, there's only the one. There's only the one I2. Right, so it's just minus 3,000, I think. And for that one, there is no constant, so it's just 0. Okay, so the next line we right, so this is going to be 20,000, and then we have a minus 3,000. Okay? So I think the coefficient here is going to be, let's try that again, is going to be 17,000. Right, 20,000 minus 3,000. I1. And then, what's next? We want I2. So I2, there's a 3,000. A 4,000 and a 5,000. Right? Exactly. So plus 12,000. I2. And what's it equal? Well, we haven't taken account of this one yet. So if we subtract, yeah, if we subtract 12 from both sides. Okay, so Next person along, can you
Yeah.
help us with...
Yeah, I'm not sure if there's other experiments there. But I think it's gonna put the numbers in the grid.
Sorry, you?
Yeah, we'll put the numbers in the grid.
Yes, please, yeah.
This is the top numbers. Yeah, I screwed up in my calculations pretty early on, so very easy.
Basically, we just want to put these two equations in.
Yeah, so it'd be number for 2,000, and then number 3,000,
Uh-huh.
and 17,000, and
Right. And well, we want 0 and negative 3. Yeah. Okay, 14 minus 14 minus 3, 17, 12. So this is 2, 4, and A equals minus 14 minus 3. And then 17 and 12. Okay, and then B equals 0 and minus 12, and then our B4 equals, and again I'm just going to do RF AB, and that should get us, so 307.7 microamps and 1437. So 307.7. Yeah, gonna have to stop that. And then I2 is minus 1437. Okay, let's go back to the top and see what we've got to answer. V out. So V out equals 5,000 I2. So we can just say that our Q4 answer equals 5,000 Q4, and it's I2 again, it's 2,3. So it's minus 7.184. And don't forget the units. Volts. Okay. The value, so 307.7 microamps and minus 1437 microamps. Format long. So if you go, the standard is format short, right? And in that case you only get that, but if you go format long, it gives you more significant figures. And sometimes it does, these aren't significant, well, it doesn't necessarily give you the right number of significant figures with all the leading zeros. So in order, I recommend you always get 4 significant figures. I've certainly seen with some of the web work questions, unless you give it 4 significant figures, your answer could be wrong. I usually give a 1% tolerance on the answers in web work, but sometimes the numerical stability of the random questions you get are a little close, so you need to give it a little bit more information. Okay. Any questions? Yeah? Okay.
For that last one, if I left it as kiloohms until I got to like the matrix part, and then I converted, is that okay?
That's okay. Just remember what you're doing and always, check what's happening. Provided you know you're working in kiloohms versus ohms, that's okay. When we get to nodal analysis, it tends to be, the algebra tends to be a little bit messier. So working in kiloohms can sometimes be a little better, because you don't have to carry as many zeros around everywhere. But you just have to make sure you're clear which way you're going. Any other questions?
What is your matrix?
My matrix.
Is that what you have in that one too?
I hope so. Is that right? 12, 14, minus 14, minus 3, 17, 12. Minus 14, minus 3, 17, 12. Yeah? And then 0 minus 12. Yeah?
I'm having some issues doing the actual matrix calculation on my calculator, but I don't seem to know how to do it at all.
Okay. Oh, so let me try to, and this won't be on the video, unfortunately. So let me see if I can. Try this up. You don't mind if I?
Go ahead.
Oh, sorry.
Yeah.
If,
I think that thing is like 7 years old now, so I do not care what happens to it.
It's okay. It's still perfectly fine for this course.
Yeah.
Let me just going to unplug that and move this over so I can see the numbers. And we might have to turn it round this way around. You want it that way. And let me just okay. There we go. That's right. Okay, so let's try and do RF. And the reason I'm recommending RF is you only need to deal with one matrix on your calculator. So second matrix, and I'm going to go over to edit, and I'm going to edit C. Right? Now when I put A and B side by side, it's going to be 2 by 3 for this one, right? So I need to make it 2 rows and 3 columns. Okay, so it's 2 by 3. And then I need to put in minus 14,000. And you can't see, but I'm just hitting enter when I do that. I figure it's better to just see. And then I'm going to enter minus 3,000. And then the next one is the 0 in B. Right? And then it's the 17,000. And then it's the 12,000. And then it's the minus 12. The thing I don't like about these particular calculators is they have a different button for unary minus versus subtract, and that always confuses me. Okay, so now I can second quit because I have my C matrix entered, and now I can go back to my matrix, and this time I want math, and I think it's B. Yeah, there we go. But I always scroll down. I don't know why. I should just hit B. But anyway, so there's RF, and then second matrix, and this time I want C, and then close bracket and enter. Okay, and that it will get you the identity matrix in the first rows and columns, or the first column. But the only thing wrong again with this one, sometimes it, depending on the numbers, you may have to scroll to the right to get the exponent. Some people get the right number, but the exponent will be off the screen, and you need to scroll across to get the exponent, to get the right. Okay? So I hope that helps. And let's go back to air media. And I think I'm going to have to reconnect, possibly, maybe. No, okay. Okay, I'm going to take a 10-minute break. I suggest you do too. And when we come back, I'm going to do the introduction to nodal analysis. Right? We won't be getting into depth into nodal analysis for another. We'll do the 4 extra questions that you have on that sheet in 2 weeks' time. We won't have time to do it today because I want to do one of the labs, the last one today. Okay, but let's take a 10-minute break now, and I'll try and fix up my pen setup. Ten minutes, yeah. Sorry, I'll put the I'll put a 10-minute timer up. You go with that. Interesting that it freezes sometimes. I could connect up to HDMI, but I prefer being over here than over there. So I'm just going to stop that and we'll start in a little bit. So just a reminder that everything I'm drawing here is available to you and should be available to you, alright? What I should be able to do is just place that here and you should all be able to access this online. So this is just in a web browser, or if you use OneNote, you should be able to access it in OneNote. So this is all just in the web browser. If you can't get access, it probably means I missed adding you. So just send me an email and but everything I've written is available to you. So if you need to go back and check. And let me just it goes. I'm just going to put a link in here. Good. Alright, so that should submit that. And I probably should make those unavailable. So now you should be able to click on that and it'll take you to that web work page. So you should also notice everybody in the class has I think Kylie dropped out, oh well, but everybody in the class has a handouts and exams page. What I'll be doing is when it comes to your midterm, I'll paste a copy of the midterm in here, the paper, and then I'll highlight things during the exam. So you won't have to have access here, but I'll be showing this on the screen when we're talking. And I just like to have notes about which questions I ask which students, and I keep all of those available in OneNote and you can see them too, at least for your individual cases. You won't be able to see everybody else's, but you should be able to see your own individual nodes as well. Okay. This checker's still going there, still going there, good. I'm going to switch gears a little bit and talk about nodal analysis. So this is just an introduction, just like I introduced mesh analysis last week. We're going to go over nodal analysis in 2 weeks' time when we come back. But I do want to introduce it now. And it's very similar in flavour to mesh analysis. The aim is to try and get analyse more complicated circuits, but rather than applying Kirchhoff's voltage law, now we want to apply Kirchhoff's current law. Okay, so the thing we're interested in is, let me just lie flat and hopefully that'll, okay. We're interested in nodal analysis. And you'll notice I have exactly the same question, right? And that's why I struck through mesh and just put nodal. But let's just have a look. Let me just see what the next page is. So that's okay. Right, so we do have that. So just like with mesh analysis, we have to identify the thing we're analysing. And whereas with mesh analysis, we need to have closed paths through the circuit that don't cut a branch. Right? A loop is a closed path through the circuit. Closed meaning it starts where it ends. But a mesh is a specific sort of loop that doesn't cut other branches. Here we're interested in identifying nodes. Right? And remember, a node is an area of constant voltage. Okay? Then we need to express the element currents. An element is a resistor, a capacitor, an inductor, as functions of the node voltages. Whereas before we started with KVL and got unknown currents, here we're going to start with KCL and have unknown voltages. Okay? So then we apply Kirchhoff's current law at each of the nodes. And I should actually modify this. Remember, in mesh analysis, the first step is identify the meshes and any super meshes. There's something analogous called a supernode. And I won't talk about supernodes until next week. But because, just think about it, the reason we use super meshes is because current sources don't tell you their voltage drop. The reason we use super nodes is because voltage sources don't tell you their current. Right, so once we've got each of the element currents defined in terms of the node voltages, then we can look at each of the nodes and apply KCL. Then we've just got a number of equations dependent on the number of nodes. We distribute in group-like terms and we plug in and solve the system. So step one, and I inadvertently chose a bad A. Right, the thing we're trying to find is VA. Normally I would label these nodes A, B in the middle and C, but because I chose A to be the middle one. Right, so this is our step one. And remember, even though I've drawn these as dots, this whole all of these are the nodes. Right? Even though I've drawn the nodes as dots, and I nearly always draw the nodes as dots, it's not just the dot. It's anywhere a wire connects to the dot is also part of the node. Okay, so then we can do the element currents, right? And I'm just going to, before we do that though, I'm going to, we have VA labelled. I would also like to label VB and VC. Just like we figure out the polarity of the voltages across each of the resistors with mesh analysis, the driving thing in nodal analysis is the polarity of the current. Right, so it helps if I identify the polarity of the current. And again, you can choose what polarity you need. It's just a matter to make sure that the passive sign convention holds and that you're consistent in application of the direction. Right, so if that one is there, and that one is there, and that one is there, and that one is there. Right, so we, oops, I'm going to get caught up in that. So the individual device currents is what we need to do next, right? So let me click on someone. Is Sonia Lease here? Yeah? Can you, for R1, can you tell us what the current through R1 is with given the voltages VA and VB? No? Okay, I'll get somebody else, that's alright. Is August here? Don't think I've seen him. Maxwell's here. Maxwell, can you... So the question is, given VB, VA and R1, what is IR1? You don't know? That's okay. So let me do the first one, right? So remember we're applying Ohm's law, V equals IR. So that means that I equals V on R. Yeah?
So you know how
I'm actually after an algebraic expression, so we'll get to the. So the voltage across R1 is VB minus VA. Right? VB on the high side because it's flowing from left to right, and VA on the low side. And so the current is VB minus VA on R1. Okay? And then let me choose somebody randomly again. AJ, you want to try telling us what IR2 is in terms of the node voltages and resistor values?
VA over R2.
So you've said VA over R2, and that could be negative VA, right? So really, here's your ground. So this side is always 0. So really it's 0 minus VA because of the direction I've chosen the current to flow. If I'd chosen the current to flow in the other direction, it would just be VA over R2. Okay? So I'm just going to make it a little less messy and do that. So let me choose someone else for R3. And, Beata, you want to have a go? Sorry. Where's this? That's correct. Right? So VA on the input side minus VC on the output side divided by, and I'm going to, on R3. Very good. And then the last one is R4. And let me choose someone else. Brianna. Right. VC over R4. Right, so again, because I've chosen the direction of the current going down this time, it's just VC minus 0 divided by R4. So it's because for R2 I chose the current going up, it's 0 minus VA on R2. Okay. So the next step is to apply KCL. So let's have a look at applying KCL. Normally I would just go across in order, and I usually go left to right. And this is one reason why we should have put in that Supernode thing. Remember, in step 1, we should have said something about identifying supernodes. There isn't a supernode here, but what there is a freebie. Just like with a current source and mesh analysis, if there's only one mesh current flowing through the current source, that's a freebie for the quote unknown unquote mesh current. if a voltage supply is only connected between the reference and a node, that means you get a freebie on the node voltage. Right? We know immediately that VB is minus 21 volts. Right? Again, you've got to remember that's the plus side and that's the minus side, so going from ground to VB is a drop in voltage. So at node B, we immediately get VB equals minus 21 volts. And then now remember we're supposed to be applying KCL. So KCL at C is IR1 plus IR2. Now IR3 is flowing out of the node, right? Here's our node, our VA. Actually that is A. I always get confused because I usually have the appropriate order, right? So this is for node A. So IR1 plus IR2, both of those are flowing into the node, but IR3 is flowing out of the node. So I tend to use the version of KCL that says the sum of the currents into the nodes is 0. You can also say the sum of the currents into the node equals the sum of the currents out of the node. Right? If I thought about it that way, then I would write IR1 plus IR2 equals IR3. Right? It's the same equation. It's just in one case I get 0 on one side, and in the other case I'm doing a balancing out. Okay, and then at C I have IR3 minus IR4 equals 0. So let's see if we can where's it doing that? Thank you, there we go. Let's go. So now let's continue with this one. So IR1 is VB minus VA on R1, which is 6 ohms, plus IR2, which is minus VA, so I'm going to change that to a minus VA on R2. R2 is 24 ohms. And then minus IR3, which is VA minus VC on R3, which is 14 ohms. Be very careful when you've got a minus sign out the front there, because people tend to forget that the minus sign out the front of VA minus VC on 14 distributes over VA and distributes over VC. So we're going to end up with a minus VA on 14 plus VC on 14. The mistake I often see is people change that to minus VA on 14 and minus VC on 14. Right, again, it's a sign. And that equals 0. And I can rearrange that a little bit Right, we know VB already is minus 21 volts. So that's going to be, oops, I don't want to do that. It's going to be minus 1/6 minus, what's it, 6, minus 124 minus 114, all multiplying VA, and then it's plus 1/14 VC, and that equals, so it's VB minus 21 on 6 negated, so it's equals 21 on 6. So let's do this one. So IR3 is VA minus VC 14. Minus IR4, which is VC on 10. Yeah. And that equals 0. And then, so I get 1/14 VA. And then I'm going to do it this way. I'm going to say plus minus a 14 minus a 10 VC equals 0. Now this particular question, there's no kilo ohms or anything. But you can see because the resistances are showing up in the denominator rather than in the numerator, it's a little bit more painful to carry around all those zeros. So sometimes it's maybe good to use kilo ohms rather than ohms, but it's up to you. If you use enough space, it's fine. Okay, so there's our equations, and I probably should have used different colours, but anyway, I'll remember to do that next time. So then we can again write a matrix equation, and this time our unknowns are VA and VC. We already know VB because we got the freebie at the beginning. So our matrix equation, and I probably should have given myself a little bit more space, but anyway, this one's minus a 6th, minus a 24th, minus a 14th, 1/14, and 1/14. Notice the symmetry coming in again. 1/14 minus a 10, because we have no dependent. Well, there's symmetry. There's no dependent sources, and then that's 21 on 6 and 0. So let's just put a closing bracket there. Right, so let's do a our A is minus the 6th, minus the 24th, minus the 14th, 1/14. I'll probably have to go back, so minus the 6th, minus the 24th, minus the 14th, and then 114. Just check that was correct. Minus 24 is 14, and 14 minus the 14 minus the 10. Okay, so there's our A matrix. Our B vector is 21 on 6 and 0. And that should give us, okay, so our VA is minus 14, and our VC is minus 5.833. And I hope you remember that that's the answer we got using just series and parallel. What was it again? Minus 5.833. Okay, so that's a quick introduction to nodal analysis, and I'm not going to go through any more examples today because I want to talk about the lab that I'd like to try and get done today. Well, we'll see. I'll give more time next time if we can't get it done. So just a quick prelude. This voltage source isn't giving us a freebie because it's connected between two non-reference nodes. And when we come back in a couple of weeks, I'll talk about how to deal with that problem. Because we don't know what the current flowing through VS is, it's not going to tell us. We need to deal with it in a different way. But dealing with it is simple. We basically decide that this whole thing is a node. And we just look at all the currents flowing into it and forget about the fact that it's not just a single area of constant voltage. You can do that because Kirchhoff's current law applies regardless. If you have a patch of the circuit, the currents flowing into the patch have to equal the currents flowing out of the patch. Otherwise you get current accumulation. But I'll talk about that next time. Okay? And next time I'll go through some more examples and then we'll do the next part of the tutorial sheet. So please bring along the tutorial sheet again. I'll put it up on the screen as well, but make sure you bring the sheet along so that we can do those as well. Okay, let's switch gears a bit and talk about Lab 3. So for each of these labs, I need to see three things. I need to see your calculations, whether you put them directly into the spreadsheet or whether you do it by hand and put a picture of your calculations into the spreadsheet. That's fine too. I need to see the LT Spice version, and I need to see the in-class version. And what we're doing with this is KVL and the voltage divider. Right? I used to have excruciatingly detailed steps about how to do all of these. And I decided to take them out because I'd rather you thought through a little bit more about what to do. And so the aim is to examine the relationship between combinations of voltage drops and combinations of resistance values in a series circuit, to measure them with respect to a common reference point, and to apply the voltage divider formula, and for you to use that formula to design a circuit. Okay, so what you must do. What I want to do today is the in-lab component. Part of the reason I didn't ask you to necessarily prepare for the LT spice is you have the right values, because even though they're the nominal values, they're not the actual values in your circuit. So what we're going to do is construct a single mesh with at least 5, and I'd suggest just 5 resistors, and a voltage supply. So what you're going to do is we're going to have a voltage supply, so this is Vs, R1, R2, R3, R4 and R5, and the aim is to validate Kirchhoff's voltage law, right? So Kirchhoff's voltage law says the voltages around that loop sum to 0, right? So Vs plus VR1 plus VR2 plus VR3 plus VR4 plus VR5 equals 0. So the things you're going to have to measure, first of all, what I probably should have put in there, let's go with black, is the ground, right? So that's the reference node. Let's erase that again and put it in properly. Right, so this is 0 volts. And then let's just label the nodes, right? A, B, C, D, and E. I usually don't label the reference node, we just call it the reference node. Now the things you're going to have to measure are the current. And remember, to measure the current, you have to break the circuit and stick the ammeter in there, right, to see what's happening. You only need one current measurement, you don't need to do lots, right, because there's only one loop, so there's only one current. You'll set it to 10 volts or 5 volts or some value, but measure it as well, just to make sure. You'll need to measure R1, R2, R3, R4 and R5. Even though you'll know the nominal values, you won't know the exact values, the real values. And then, if you're going to validate this equation, right, you want to measure go with blue again. You want to measure the R1, the R2, the R3, the R4, and the R5. And once you've got all of those things, you should be able to validate that this is true. Now, because of measurement inaccuracy, it might not be exactly 0, but it should still be pretty small. If it ends up being more than about 0.1 volts, you've probably made a mismeasurement or you've got the sign wrong. So remember, I've defined my current direction. So that means the polarities of all of those voltages are like this. So in order to measure that properly with the meter, right, if I have a voltmeter, then I need to put the red probe on the plus and the black probe on the minus side. That way you should get the right sign. And that's about it for the first part. So the second part, let's just zoom in. I want you to design a voltage divider. And the voltage divider has to take in 15 volts. So that's 15 volts. And it has to give out 3.5 volts. And remember, that's going to be equal to R2 divided by R1 plus R2 times 15. So you have to choose R1 and R2 so that that's true. In this case, we only have 12 different coefficients for the resistors. So in this case, you're probably not going to be able to hit 3.5 exactly. Right? It should be 3.6, 3.4, something like that. You can hit 3.5, I'll tell you, you can. But it depends on which values you choose for R1 and R2. Because once you've fixed one, that fixes the other one to get 3.5 volts, but that other one might not be available in the nominal values that we have. Right? Everybody understand the problem? So what I'm going to do is I'm going to go and get 5 or 6 different resistor value boxes and put them up here. And I might just move that room. And you can figure out which piece of lab equipment. To make life easier, I haven't been really, for labs 1 and 2, I haven't been a stickler for the equipment numbers. I'm going to start being a little bit more pedantic as we go forward. So if you keep the same units, that way you always know what your equipment number is, right? You don't have to keep looking at it. So try and keep that. Remember the take a number URL is available in the lab section of Blackboard, so if you need help. I'm going to have to open up the next room as well because we don't have enough spots here, but so I'll be between the 2 rooms. Let me get the resistors and you can come and get them. I'm sure it's set up at your place. So I have chosen values that all have the label. So, but be aware that sometimes what's in the box is not the right number. And I might go and get a different tube because I don't know if we're getting enough. So I've got 6 boxes here, you only need 5 resistors. So choose, you could choose one from each, or you could choose, but just choose 5. And I will go and open up the next door.
I think so. That's what I'm going with. Find out and see if it works. Don't know what step it is.
You said the numbers are on them? You have to double check it.
they all necessarily have to be different resistors?
No, you can have the same ones if you want, but I have some different ones.
Yeah, I'll keep two the same.
Yeah, that's okay.
Yes, I think one of them has to be from this one, because these ones are really unfair.
27 inches?
Number 28 is it? Okay, number 28, okay? 31? 31? Yeah, it looks like okay. Right, so before we do that, the first thing I do is measure all the distances. Okay? And with these, so the black tree is always the and then the red tree is the top, measuring all the voltage or resistance. And then the red tree is at the bottom, which is measuring top. Okay? So the first thing I do is measure the resistance. Because even though it's randomly, it's randomly on top, some of these factors on top. So I need to measure it right now. But I didn't do that. So something like that. And that's just cool. Yeah. I need to know that. So you have to all of these files are connected together. So to make this electrical connection in series, it has to be in one of those files, other four in that level. And then, that's correct. Should I do another one? No? So, you could just keep going yourself, right? No, I would tend to just make this one go over here. Right? So let's just take the next one here. And then we need another one for another one. And we can electrically connect that one up. Because it's got to be in row 5. Same row 5 as the previous one. Right? And then the last one the only trouble is, all of those are all connected together. So if this comes in the red one, you don't want to put this one in. You don't want it connected to, you don't want it connected to something. Now, it's sort of a bit fast, so what I suggest is taking all this out and measuring it individually. You may be able to make things out if there's no connection, but I have seen them taken out and no, it doesn't matter because it's only one set. So provided you take the same area you only need to take that one. Number 32. 32.
Yeah.
So these two are electrically connected to the from each power.
Number 33? Number 33.
Yeah.
Number 33? Yeah, so. Okay. 34? No? I might have this number 34?
Yeah. Well, my problem with using
It's your turn. It says it's your turn.
I've got
Okay, so let's, if you need a assistant resistor, so let's grab that 3.2. You don't have to have 3.2, you do have a 3.3. Oh, just the right. That's close enough. That's close to it. Is that today? Okay. 26 in here? Right, 26? Is that? If that's all you've got, that's all you need. Remember, you need to do the other styles here. Okay, thank you.
What's up? And there. Labs. Objective release. Okay. Objective release.
That's probably quite a few. Yeah, here. 939.
Go ahead.
Number 40.
Oh, that was actually the last one. Yeah.
Number 41. Number 41. Right, so, have you done a calculation? Right, so and I don't know whether this is the idea is that you just
some of them, because of the resistors, you've got even four, 42. 42. Number 43? No? 44? Anybody closer here? No? Okay.
So it's just I see like two
possible ones. Yeah,
right.
I think it's definitely one of these.
Yeah. I'm gonna go with this.
You guys playing color matching game?
Yeah.
Okay.
It's going slow. That's not it. Okay.
Blue, green, red, gold, green, black, gold, green, and orange. Supposedly this is one code. I don't believe that for a second.
What don't you believe for a second?
I don't even know how I got a 100 ohm resistor.
No, I don't know how either. It's probably in the wrong box.
Yeah, because I just put
This
one
one had a
back.
bunch of them mixed. Like,
Yeah, that one does look like it's pretty mixed. There's 2.2K there.
Oh yeah. Okay, well so this should be a 1K, right? That's labeled 1K.
Yeah, that's 1K. That is 1K.
Awesome, great, thank you.
49? Note 49?
The three part numbers and stuff. Yeah, so it was good. I would use the same ones, but as long as you've got it.
Good tweaks.
See you next class.
about 2 weeks now.
You like see you
Yeah.
No, I didn't call.
Oh.
I don't call.
Professor, do you know what the student center is the architect? I just missed it.
Well,
Thank you, Professor. You're good, right?
yeah, till it's done.
Professor, one of my resistors broke. I just left it on the desk.
That's okay. They do that. They're pretty cheap.
I said, no, no.
Yeah.
I said that I was finished using it, but.
Yeah, that's okay. Thank you. Yeah, you too. Well, I'm gonna email it to you. Yeah, see ya.
So,
Don't suppose you know Dan?
Dan? Nope.
The guy, I think he was the guy who was there to your left. He apparently left his calculator.
Oh, I don't recognize him actually. I don't,
Yeah.
Masks make everything hard.
Yeah, I know. It's a pain.
None of these are red, orange, orange.
No, just leave it out here.
Okay. And this is my one. Okay. So I think I have everything.
Okay.
Yeah, I should be alright. If I missed anything, there'll be more time next week, right? If you need it.
Well, not next week. 2 weeks
Oh, 2
time.
weeks from now.
Yeah.
Next class.
Next class is fine. Yep.
Okay. I'm just gonna go clean my station.
So if you go into the syllabus might have it, but just go into Blackboard and Tools for Remote Work and go to Bookings and just book a general consultation.
Okay.
And if you scroll down,
It'll show you time.
it'll show you the dates I'm available and the times over here. Okay?
Thank you.
You're welcome.
That just makes sense.
Thank you. Yeah, you too. We're all good here?
analysis today made a lot more sense than the first time.
Oh, really?
And I actually got it this time. Because the first time I was like, what the heck? And now it makes sense. 'Cause I was having trouble like linking the linear algebra part to the actual concept. But then like once it was explained, like we're just setting up a system of equations, all you have to do is solve for it and then you're done. And then, it's very quick as well.
And I found I need to say the same thing several times, sometimes different ways,
Yeah.
in order for most of the class to get it. But it all depends. So
Yeah.
that's good.
Good. All right. I'll see you in 2 weeks.
Yep, see ya.
Have a good one.
Okay. Wonder who's confused. We'll go and leave that. Well done?
Eleven. Looks like we've got them all mixed up.
Yeah. Try matching the label if you can. So that's 1K. Doing that one. And that one is a 56K, oh, 5K6 rather, sorry. And that's a 4K6. All good? Cool. Thank you. Yeah, you too. See you in a couple of weeks. I need to put the right. Okay. Let's see. Junk. Up.
Well,